Hello together. Our topic today is advanced high-strength testing, and we would like to demonstrate and to explain a little bit how that works with Zwickrell instruments and testing machines. Now, how high advanced strength steels are special steel alloys which dedicated to automotive application and are dedicated more or less for lightweight constructions. This is a main topic. So if the quality is tested or has to be tested from these high strength steels, then sometimes you have quite tiny samples, specimens, and they have to be tested very reliable, of course. And just to see these small specimens, I have brought one, for example, this one here, and a typical other sample is a little bit bigger one. This is a typical type 1 specimen from how it is explained in the ISO standard. So these are difficulties to measure these very reliable. And what is your experience, Karin? Is this a real topic in testing area?
Yes, for sure. I totally agree. So what we have in the lab from our experience, the samples are always getting smaller, especially the shoulders are getting smaller. They are built from the parts, so this is sometimes really a problem for gripping.
Yeah, so this is the reason why we have think about the right gripping technique. So first of all, if you have a high strength material, then this means also that the surface is hard and not soft. So this means that you have to have high forces, or means high clamping forces, to clamp the grips, or the sample with the grips from the very beginning on very tight, to avoid any slipping and so on. So, but in this case, for example, it is quite difficult with a testing machine with a normal gripping to grip this precisely enough and avoiding particularly the slipping. So what happens if you are really going for this kind of material? So first of all, you should really grip on the entire surface of the sample heads. So you should avoid that the inserts of the grips are tilted during the test. So this direction, for example. So how to avoid this? If you have these tiny, for example, specimens, which are just having an overlap on a certain part only. So what happens during normal sample holders or gripping procedures? So if you are clamping on these tiny edges, then during the gripping process, these inserts will tilt it. And then, of course, you will not have the full force and the full pressure on the entire surface. And this means that you have only a gripping force and a sample hold it by one line at this end, for example. This means that there is no good contact to the inserts anymore, and the sample will slip out. And the second point is, of course, that the wear off of these inserts are quite dramatic. So these are the points. First is having a tight gripping, avoiding the slipping, and the second is the wear off with these very hard and high strength material which is affecting the inserts. So, Karin, what are your experience if you are testing this high-strength material and especially these tiny samples with normal standard grips, let's say?
So for the very, very short shoulder, for sure, this is really hard. Normally, you should think about a special jaw phase when the maximum stress is higher than 1000 megapascal. And therefore, you at least need special grips.
Yeah. So now the question is how to get rid of these kind of problems. And we developed a special hydraulic grip which keeps these inserts parallel, independently what happens during the test and during the clamping process. So how is that working? So if you have the sample clamped, maybe here on this level, so normally it would be tilted, as I said already, but we developed a system which brings a second force on this side, on the opposite side of the clamped specimen. So this is realized by a third cylinder. So if we go to this setup here, then you see there is a device here which is the third cylinder which stabilizes the movement of these inserts. So this is done inside the hydraulic system and it works completely automatically. So this is, I think, very easy to operate.
Yes.
And can we operate it just by test expert, or have we anything to do to ensure that the system is really running as we would like to do?
No, everything is operated by test expert. You are using the remote control to grip the sample, and then later on when you start the test, you set the pressure for the main pressure for the test. But this is something I can show you later during the test.
Yeah, so now we talked about this gripping system. Now if you look to the total setup, this is a quite standard setup. Testing machine, load cell, the gripping system, but then we also have a special extensometer system which we call laser extens, and this is the optical, of course, strain measurement, and this is working without any markings to the sample, like this one. There is nothing to do concerning marking, and this is done, or this is provided by the very strong laser light. The laser light creates a certain speckle in the area, and these speckles are more or less fingerprints of the surface, of the texture of the surface, of the roughness of the surface, but very individual. So, and these speckles are moving if this specimen is stretched and strained. And this moving one can use for measuring the strain from the very beginning to the end of the test, means up to break and failure of the specimen. So one question maybe can come up: how precise is this kind of optical measurements, strain measurement? So this device here, this laser extends, is going down to class 0.5, means it's a very accurate strain measurement instrument. So I think we are ready with these some explanations for test. Karin, would you start?
Yes, for sure.
With the test?
So I've already measured the sample, so now I will show you how we grip the sample. As I said before, we have the remote control. With the remote control, we are closing and opening the grips. For sure, first of all, we are closing the grip which is mounted on the load cell. At this point, we are zeroing the force. And during the closing of the lower grip, in this case, we have the activated so-called force zero control, so the force is always kept to zero which is important because in the standard it's written that we should not exceed more than 5% of the expected RP or REH value.
Yeah, right. So we have to avoid any pre-damage of the sample.
That's it. So I'm closing now the lower grip and maybe give you a better view. So I will now zoom into this point. We have the upper grip, the lower grip, and what you really nicely see here is the laser light on the sample.
Yes, and if you look a little bit closer, then you see even the speckles. This is the texture you see in the lights coming back to the camera. So, and just to imagine, it's really laser light. If you go with a finger, then you see the different structures from the different laser diodes, and this is a real laser light showing what happens with the reflected light from the specimen. So I would like to mention one point. You see in the lower part of the picture very clearly, so I took the sample to show you that what I mean. This tiny thing here, this is a stopper, and this is a quite important point that you have to use it and to apply it, because the sample should of course be in line of the forced trail. So it should be aligned. Not only the machine should align, but the test piece also should be aligned very precisely in the grips. Otherwise we have of course bending effects and non-alignment effects.
Yes, so I think at this point it's a good point to change to test expert to show how this sample now looks in the laser extend software. You see the window or the frame is angled, turned 90 degrees to get the whole range of the sample, and this is how it looks like. So the green windows here is nothing else than the gauge length, which we have adapted to 50, which is mentioned in the standard to use 50 on this kind of samples. We can move this, and you see here it's 50, but for sure it's automatically set before the test because the input is 50 mm in the software. So should I start?
Oh yes, please. So if everything is prepared, of course, then there's only a push button necessary to start everything, and then test is going on. So while the test is proceeding, I would like to talk a little bit about testing speeds and the control of strain rates. So we are of course applying the ISO 6892 Part 1 methods. We could drive the system via the stress rate based method. This is method B, and also with a strain rate method. This is method A1 and A2. So at this moment we apply method A1. So this gives us a quite precise, very stable strain rate over the very important beginning of the test. And this is realized, this precision, with an adaptive controlling of the drive system, of course, which is comparable with a let's say machine learning system. The machine and the test control is learning by itself how the sample is behaving in the testing system, so that it could be adapted to the different situation automatically. This means it arrives the set values very precisely and also very quickly. So this is an automatic compromise which is done by an adaptive system. So the important point is why we need this quite good test speed control, because the materials are sometimes quite heavily depending on the testing speeds, and if you look into more details, then this is the strain rate which is influencing the values, specifically the yield point and the RP values of the material. So let's take a look to the stress strain curve. Karin, I think what is the first thing if you have a look to these stress strain curves? The standard is recommending something which is related to the initial slope.
Yes. So what I would do is here having a zoom of the beginning, and as you see here, the initial slope is perfectly on the stress strain curve.
Yes. So if this would not be the case, what are the measures you can take to make this proper? I mean, sometimes the people do not do it automatically. They have certain stress values in between the slope is calculated. What are the basic measures?
So in this case, I have set to calculate the slope via regression, which is also mentioned in the standard to do so. And what you say here is you just check out if the settings for the begin and the end, which I have used now with 100 and 300, are matching your sample here where you have really the slope.
Yeah. So means if this is not the case, then we have to look in detail if the parameters are setting correctly. So this is an important point, and this is also a kind of, let's say, quality check if the test is really done properly. Yeah? Sometimes it happens that this is a different case. So this means we have done a visual check, and this check shows this everything is okay.
Yes.
Now I have another question. We changed the speed during the test, of course. We have 3 test phases. The first one is the elastic part until the yield strength or the yield point, and then we switch to another testing speed, and the last phase is the testing phase. How is this done, these switching points in TestExpert? Do you have strictly to preset it, or is TestExpert reacting on what you are generally telling TestExpert?
So TestExpert is reacting what we say. First of all, maybe I show how we set the different phases, and these are the phases which are mentioned in the standard. And when we come to the speed switching, we define the end of the test phase yield point to the plastic strain, and therefore it's also possible to measure not only RP02, maybe some customers want to have the RP05, and then you can easily adapt this to your last RPX value you want to determine.
Yeah, and the other possibility, of course, would be that you do the test with only one test speed as well.
Yes.
So
yes.
You have the freedom to say to the program at which point the testing speed and what testing speed should be applied to the testing, to the specimen. Yeah, fine, very good. So if you go back to this stress strain curve, the last one, then we see something which looks at the first point a little bit strange, because we have maybe not seen the break within the gauge length. So, and this happens from time to time. And now what can we do if we have definitely a failure, a break outside of the initial gauge length? Because normally the test then is invalid and has to be repeated.
Yes. So first of all, I maybe want to show live the sample break, which was not in the middle, maybe close to the gauge length.
Yeah.
So this is the truth, what we see here. And now I can show you, we have something which is called test rerun. So what I'm now doing is I have a look. So we have saved the pictures or the frames during the test of the laser extents. And now we are able to see or to evaluate the sample by changing the gauge length to the part where we have the break in the middle.
Yeah, let me understand it again. So you are saying that this doesn't matter generally.
Yes.
So because the system here is not just measuring the strain, but it's also recording the whole process.
Yes.
So this means that if we know the whole process, all the pattern along the entire specimen, then afterwards we can just move these measuring spots or measuring positions and change this to the place we really need. So this is more or less the same as we would have
if we measure manually.
Set the initial gauge length just around the break and the failure.
That's it.
So this is dramatically, yes. So this helps us really to avoid any tests or repeat tests which failed just by having the failure or the break outside a fixed gauge length position. Yeah.
Let me show you. So now I'm moving the frames. And as I said, the break was very close to the gauge length. So what I'm doing now is, just a second, I need to make a setting. So now I'm moving the gauge length. Where I had the break, let me check again. So the break was here, you can see it.
Yeah, just around the break, and again,
and
50
I'm
millimeter
moving
gauge
to
length.
50
Yeah, so this has to
gauge
be
length.
manually adjusted,
for sure,
of
this
course.
has to be manually.
Yeah.
Oops.
So and then
I'm starting the test again.
yeah,
But
everything.
it's somehow a virtual test.
Yes, this is the recalculation of everything. Yeah, with these new position of, let's say, the feeler position.
And
And
now
then-
you see here, and it's really obvious also for sure in the strain at break. So we had 3.9 where the break was close to the feeler arm or the gauge length. And now we have recalculated with 5.8.
So this is for this kind of material a difference between, let's say, nearly 4 and nearly 6%. This is, of course, a lot for these kind of high-strength steels.
Yes, for sure.
Yeah, and this helps to avoid, doing additional tests and save time, save money, and so on. So this is quite nice. So let's maybe talk in the end about the total system. So we have to stick with the we have to stick to first to the laser extensometer again. So we have the big advantage that we are really looking to the entire sample, specifically to the entire parallel length, so that we can detect and measure the failure and the breaks, even could measure the strain if the break is outside the initial positioning of the gauge length. And the second, maybe also very important thing, is there is no influence from the extensometer to the specimen, and the specimen also is not influencing the measurement, how it could be in the mechanical options. So, and the other point is, of course, we can measure up to break even with these high-strength steels, which really have a hard break and so reduce any damage or any influence to the system. So this means we are having a system which is very rigid, very reliable. The wear off is very, very small, and this is really dedicated to high strength steel in general. Even if you have these kind of small samples, it's also possible to measure these kind of things. So, this is our approach to make this application. Mm-hmm. And Karin, what is your experience in the end? Do you like this kind of system?
Yes, for sure.
For sure.
For sure.
Fine. Then, thank you very much.
Thank you.
Looking to us and listen to us, and see you next time. Bye-bye.
Bye.